Hello class, today I want to speak about Newton's law for universal gravitation. It was said that Newton first suggested the idea of gravity when an apple fell on his head. Then he extended the idea to all objects that have masses. So if you have two objects, let's say A and B, of respective masses m1 and m2 and separated by a distance r apart. Then, according to Newton, there is a force of attraction between them. B exerts a force on A, which is force B on A, and A exerts a force on B, which is Fa on B. These two forces are opposite in direction and equal in magnitude according to Newton's third law. Their common magnitude, according to the law of universal gravitation, is equal to a constant g times the mass of the first body times the mass of the second body divided by square the distance between them. Now, F is in Newton and R is in meters and the masses are in kilogram. The accepted value of G is equal to 6.67 times 10 power minus 11. Okay, so this is a Newton times meter square divided by kilograms square. Now, by applying Newton's law for universal gravitation, we will find the expression of the gravitational acceleration gz at an altitude z. So if we have an object like the moon orbiting about the Earth at an altitude z. So we have the Earth and the moon. So the moon of mass small m and the Earth of mass big M orbiting, and this is the moon orbiting about the Earth at an altitude z from the sea level. Okay, and this is the radius of the Earth. Now we can neglect the radius of the moon as it is small compared to the radius of the Earth. Okay, then according to Newton's law of universal gravitation, the force of attraction, the magnitude of this force between the moon and the Earth is equal to the constant g times the mass of the moon times the mass of the Earth divided by square the distance between them, which is the radius of Earth plus z plus the radius of the moon, which we can neglect. So this is r plus z square. Now this is the force of attraction between the Earth and the moon, which is equal to the weight of the moon itself, which is the force exerted by the Earth on the moon. So the weight of the moon is equal to the mass of the moon times g z. Now these two forces are the same. Basically, this is the same force. So g times m over r plus z square is equal to the mass of the moon times the value of gravity at altitude z. Dividing m from both sides of the equation, we get the value of the gravity at an altitude z. This is equal g times m over r plus z square. This equation tells us that the value of gravity at a special altitude z is only related to the altitude itself, as g, m and r are all constant. So the value of gravity at a special altitude depends only on that altitude. So gz is expressed in meters per second square. Okay, g we already derived it, and the mass of Earth is expressed in kilogram. R and z are expressed in meters. Now if you want to take a special case where the object is on the surface of Earth, okay, that is z is equal to 0. Okay, we want to find g0 where z is equal to 0. So we want to find the value of the gravity at the sea level where there is no altitude. Okay, so if the object was here, for example. Okay, so there is no altitude, only there is the radius of Earth. So g0 is equal, we get it from here, this is g times m divided by r plus 0 square. So this is r square. Now we want to find a relation between g0 and gz. That is the value of gravity at sea level and the value of gravity at a given altitude, because we want to use this equation in the satellite motion. So this is the relation between g0 and gz. So gz is equal to g times m, okay, and g times m from this equation is equal g0 times r square divided by r plus z square. And this is a relation between the value of gravity at an altitude z and the value of gravity at sea level, and this equation is going to be used in the satellite motion. This is everything for today.